You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Performance engineering is the discipline of designing artificial intelligence systems so that they can operate efficiently and reliably under real-world conditions. While accuracy and safety often dominate discussions about AI, the ability of a system to respond quickly, scale to millions of users, and manage resources responsibly is equally important. A model that generates correct answers but does so slowly, inconsistently, or at unsustainable cost is not viable for production. Performance engineering addresses this by focusing on throughput, latency, and utilization, ensuring that systems are not only intelligent but also practical. It applies principles from software engineering, distributed computing, and systems design to the unique challenges posed by large AI pipelines. In doing so, it transforms theoretical advances into usable infrastructure, making it possible for organizations to deploy AI at scale without sacrificing responsiveness, stability, or affordability. The definition of performance engineering in AI centers on the optimization of throughput, latency, and resource utilization. Throughput measures how many requests a system can handle in a given period, while latency captures how quickly it can respond to an individual request. Resource utilization reflects how efficiently CPUs, GPUs, memory, and network bandwidth are consumed. Balancing these three dimensions is challenging, as improvements in one often create trade-offs in another. Performance engineering therefore involves designing architectures, workflows, and optimization strategies that balance these goals in ways aligned with user needs and organizational priorities. By taking a holistic view of performance, engineers create systems that remain resilient even under heavy demand, enabling AI to function as an integral part of enterprise operations rather than as a fragile, resource-intensive experiment. Performance engineering is especially important in AI because large models and complex pipelines impose heavy computational demands. Modern language and vision models often require billions of parameters and multiple stages of processing, from retrieval to generation to post-processing. Without careful engineering, these systems can become bottlenecks, introducing latency that frustrates users and driving costs that make deployment unsustainable. In customer-facing applications like chat assistants or recommendation engines, responsiveness is directly tied to user trust and satisfaction. In back-end systems like fraud detection, delays can create security risks or compliance failures. Performance engineering ensures that these systems remain usable, responsive, and scalable, making the difference between a proof of concept and a production-ready solution. Caching is one of the most fundamental strategies in performance engineering, relying on the principle that reusing previously computed results is faster than recomputing them. Many AI tasks involve repetitive queries or overlapping contexts. For example, embedding vectors for common words or documents can be cached rather than recalculated, saving both time and computational resources. Similarly, retrieval results for frequently asked questions or generated responses to common prompts can be stored and served from cache. This reduces redundant work and improves responsiveness. Caching is especially valuable in high-traffic systems, where even small savings per request compound into significant overall improvements. By reducing computation for recurring tasks, caching reduces both latency and cost, making AI systems more sustainable at scale. There are several types of caching strategies used in AI systems, each targeting different points in the pipeline. Embedding caches store vector representations of text or images, avoiding recomputation when the same inputs reappear. Retrieval caches store the results of database or search queries, ensuring that repeated lookups do not hit the backend unnecessarily. Response caches store complete model outputs for common prompts, allowing instant replay of frequent answers. Each type has different trade-offs. Embedding caches save compute but require memory, while response caches can reduce latency dramatically, but risk serving stale answers if the model or context evolves. Choosing which caches to implement, depends on workload patterns and tolerance for outdated results. Together, these strategies demonstrate the versatility of caching in, enhancing performance across the entire AI pipeline. The benefits of caching are significant, making it one of the most cost-effective optimizations in performance engineering. By reducing redundant computation, caching lowers GPU and CPU demand, directly cutting infrastructure expenses. It also improves latency, since cached results can be delivered almost instantly compared to recomputing them. This translates into smoother user experiences, particularly in interactive applications like conversational agents. Caching also reduces strain on supporting systems, such as databases or retrieval engines, by offloading repetitive queries. In enterprise environments where scale magnifies every inefficiency, caching can be the difference between feasible and unsustainable deployment. While it may seem like a simple optimization, caching often delivers outsized improvements, underscoring why it is one of the first strategies engineers implement in performance-sensitive systems. Batching is another cornerstone of performance engineering, designed to process multiple requests together rather than individually. Many AI models, particularly those running on GPUs, achieve higher efficiency when workloads are grouped into larger batches. By batching requests, systems maximize parallelism, reduce overhead, and improve overall throughput. For example, instead of processing 10 user queries one by one, a system may process them simultaneously as a batch, significantly reducing total processing time. This approach leverages the strengths of modern hardware, which is optimized for vectorized and parallel operations. Batching is especially effective in back-end systems where latency requirements are less strict, allowing requests to accumulate briefly before processing. By aligning workload patterns with hardware capabilities, batching turns potential inefficiencies into opportunities for optimization. The advantages of batching are clear when viewed in terms of GPU utilization and cost efficiency. GPUs are powerful but expensive, and maximizing their use is essential for sustainable AI operations. By feeding them larger batches, engineers ensure that hardware resources are used effectively, minimizing idle cycles and wasted capacity. Batching also reduces per-request overhead, since loading data, initializing computations, and writing results occur once for many requests, instead of separately for each. These efficiencies reduce overall infrastructure costs and increase throughput, enabling organizations to serve more users with fewer resources. In contexts like recommendation engines or content filtering, where requests naturally accumulate in high volumes, batching delivers particularly strong returns on investment. Despite its benefits, batching also introduces limitations, particularly for latency-sensitive applications. Because batching requires waiting for multiple requests to accumulate, it can add delay for individual users. In interactive systems like chat assistants, even small delays can disrupt the perception of responsiveness. Batching also requires careful management to avoid creating unfair queues where some requests wait disproportionately longer than others. Engineers must balance batch size and timing, optimizing for both throughput and latency. In some systems, adaptive batching strategies are used, where batch size grows or shrinks depending on traffic. These trade-offs highlight the complexity of performance engineering, where optimizations must be tailored to context rather than applied uniformly. Streaming outputs address latency challenges by delivering results incrementally rather than waiting for full completion. Instead of holding back until a model has generated an entire response, streaming sends partial outputs as they are produced. For example, a conversational AI may stream sentences word by word, allowing users to read responses in real time. This improves perceived responsiveness, as users see progress immediately rather than waiting silently. Streaming also enables interactivity, as users can interrupt or redirect a system mid-response. From a technical perspective, streaming requires pipeline adjustments to support incremental delivery without compromising coherence. While it does not reduce total computation time, it transforms the user experience by minimizing waiting. Streaming demonstrates that in performance engineering, perception can be as important as raw speed. The benefits of streaming are especially evident in user-facing applications. By providing incremental outputs, streaming reduces frustration, increases engagement, and builds trust in the system. Users perceive streamed responses as faster and more natural, mirroring human conversation. Streaming also supports accessibility, as responses can be read aloud or displayed in real time, reducing barriers for users with diverse needs. In enterprise settings, streaming can improve productivity by delivering partial results quickly, allowing users to act while full processing continues. These benefits extend beyond speed to the overall experience of responsiveness, reminding engineers that performance is not only a technical measure, but also a human perception shaped by design choices. Concurrency is the principle of processing multiple requests simultaneously, ensuring that systems can serve many users at once. In practice, this involves parallelizing tasks across CPUs, GPUs, or distributed servers. Concurrency allows systems to maximize utilization of resources and maintain responsiveness even under heavy load. For example, a recommendation system may process thousands of queries simultaneously, ensuring that no single user experiences delay due to others' requests. Concurrency is essential for scalability, since real-world systems must serve diverse and unpredictable traffic patterns. It requires careful engineering to balance workloads, avoid bottlenecks, and ensure fairness. By enabling parallelism, concurrency transforms limited resources into scalable platforms capable of supporting global user bases. The challenges of concurrency stem from the complexity of coordinating parallel processes. Race conditions, where multiple processes attempt to update the same resource simultaneously, can create errors or inconsistencies. Resource contention, where processes compete for limited bandwidth or compute, can degrade performance rather than improve it. Concurrency also requires robust synchronization mechanisms to ensure that results remain consistent across distributed systems. Engineers must carefully design pipelines to avoid bottlenecks, deadlocks, or unfair prioritization. While concurrency is a powerful tool for scaling, it magnifies complexity, requiring sophisticated architecture and monitoring. Successful concurrency design turns potential chaos into structured efficiency, enabling systems to handle growth without collapse. Monitoring performance is essential to ensure that caching, batching, streaming, and concurrency operate as intended. Telemetry systems collect data on latency, throughput, error rates, and resource utilization, providing visibility into system health. Monitoring allows engineers to detect bottlenecks, diagnose failures, and evaluate the impact of optimizations. For example, if latency spikes after increasing batch size, telemetry reveals the trade-off in real time. Performance monitoring also supports compliance, as enterprises must often demonstrate that systems meet service-level agreements. Without monitoring, performance engineering is guesswork. With it, optimization becomes evidence-driven. Monitoring thus provides the feedback loop that turns performance strategies into reliable, scalable practices. Scalability concerns tie all performance engineering strategies together, since the ultimate goal is to ensure that AI systems remain functional as user bases expand. Techniques like caching reduce redundant work, batching maximizes resource use, streaming improves responsiveness, and concurrency enables parallelism. Together, these strategies allow systems to scale from hundreds to millions of users without collapse. Scalability is not simply about adding more servers. It is about designing systems that grow efficiently. Poorly engineered systems may scale linearly in cost, making growth unsustainable. Well-engineered systems scale sublinearly, allowing growth in users without proportional growth in expense. Performance engineering provides the tools to achieve this balance, enabling AI to support real-world demands sustainably. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Latency and throughput are two of the most important measures in performance engineering. Yet optimizing one often comes at the expense of the other. Latency refers to the time it takes for a system to process an individual request, while throughput measures how many requests can be handled over a given period. Increasing throughput by batching requests or maximizing GPU utilization may add waiting time for individual users, raising latency. Conversely, optimizing exclusively for low latency, such as by processing each request immediately, can reduce throughput because resources are underutilized. The challenge lies in striking a balance that aligns with user expectations and business goals. For interactive applications like chatbots or search engines, low latency is paramount, while back-end systems such as fraud detection pipelines may prioritize throughput. Engineers must therefore design systems flexibly, understanding that no single optimization is universally best. Instead, trade-offs must be managed thoughtfully, depending on the application context. Load balancing is a cornerstone of performance engineering, ensuring that user requests are distributed evenly across servers or compute nodes. Without effective load balancing, some servers may become overloaded while others remain underutilized, leading to inefficiencies and degraded performance. Modern systems often use dynamic load balancers that adapt traffic distribution in real time, accounting for server health, geographic location, and network conditions. For example, a global content delivery system might route traffic to servers closest to users to reduce latency, while also redistributing requests if one server shows signs of stress. Load balancing is not just about efficiency. It also improves reliability by preventing single points of failure and ensuring that services remain available even when individual servers falter. In large-scale AI deployments, load balancing is essential for maintaining responsiveness and cost efficiency across complex, distributed infrastructures. Resource allocation refers to the process of distributing computational resources like CPUs, GPUs, memory, and bandwidth in ways that minimize bottlenecks and maximize efficiency. In AI systems, GPUs are often the most valuable resource since they handle the intensive computations required for inference. Proper allocation ensures that GPU workloads are balanced, memory is managed effectively, and CPUs support pre-processing tasks without creating slowdowns. Resource allocation can also extend to cloud environments, where organizations dynamically assign resources based on demand, scaling up during peak hours and scaling down during lulls. Misallocation, by contrast, leads to idle hardware, wasted costs, or bottlenecks that frustrate users. Effective resource allocation requires both predictive planning and real-time monitoring, ensuring that infrastructure matches workload needs as closely as possible. In practice, this can mean configuring pipelines to optimize GPU usage during batching or adjusting server clusters to align with changing traffic patterns. Asynchronous processing is another key technique in performance engineering, enabling systems to handle more requests simultaneously by avoiding unnecessary blocking. In synchronous workflows, one task must complete before the next begins, creating idle time while waiting for results. Asynchronous processing allows tasks to proceed independently, freeing resources to handle additional requests while previous ones are still in progress. For example, a chatbot might continue processing new user queries while waiting for a database retrieval step to complete. Asynchronous designs are especially powerful when combined with concurrency, allowing systems to serve many users without requiring linear scaling of resources. However, asynchronous systems are more complex to design as they require careful coordination to ensure consistency and avoid errors. Done well, they unlock significant efficiency, transforming idle time into productive work and improving responsiveness for end users. Queue management is closely tied to asynchronous processing, as it organizes how incoming requests are prioritized and scheduled. Queues act as buffers, ensuring that systems handle workloads fairly and predictably, even when traffic surges. For example, a fraud detection system might prioritize real-time transactions for immediate analysis, while scheduling batch audits during off-peak hours. Queue management also prevents resource overload by smoothing demand spikes, distributing work more evenly over time. Sophisticated queue designs can incorporate priority levels, deadlines, or fairness policies to ensure that no user or request type is consistently disadvantaged. Poor queue management, by contrast, can create bottlenecks, long delays, or unfair allocation of resources. Well-engineered queues therefore form the backbone of scalable, reliable systems, turning chaotic incoming traffic into orderly, manageable workloads that align with organizational priorities. Compression techniques provide performance gains by reducing the size of data transferred or stored during AI workflows. Intermediate results, such as embeddings or retrieved documents, can be large, consuming bandwidth and memory. Compressing these representations reduces strain on networks and storage systems, speeding up communication between components. For example, compressing embedding vectors in a retrieval pipeline allows more results to be transmitted quickly, improving responsiveness. Compression also reduces costs in cloud environments, where bandwidth and storage often drive expenses. However, compression must balance efficiency with accuracy, as overly aggressive techniques may degrade the fidelity of results. Engineers must therefore select methods that preserve the critical information needed for downstream tasks while minimizing data overhead. Compression illustrates how even modest technical adjustments can compound into significant performance improvements at scale. Edge deployment offers another powerful strategy for performance optimization, particularly in latency-sensitive applications. By placing models closer to users, either on local servers or devices, organizations reduce the time required for data to travel to centralized servers and back. This geographic proximity improves responsiveness, enabling near real-time performance even in bandwidth-constrained environments. For example, voice assistants deployed on edge devices can process simple commands locally, reducing reliance on cloud servers for every query. Edge deployment also improves resilience, as systems remain functional even when connectivity is limited. However, edge resources are often constrained compared to centralized data centers, requiring models to be optimized for efficiency. This trade-off means organizations must decide which tasks to process locally and which to send to the cloud, balancing speed, accuracy, and resource availability. Edge deployment reflects the broader principle of aligning infrastructure with user needs, delivering performance where it matters most. Evaluation benchmarks in performance engineering provide structured ways to measure whether optimizations achieve desired outcomes. Metrics such as latency, throughput, and cost efficiency form the core, but more nuanced measures may also be included, such as resource utilization rates or user satisfaction scores. Benchmarks provide accountability, ensuring that changes are not just theoretical improvements but deliver measurable results under realistic conditions. For example, a benchmark test might simulate thousands of concurrent requests to assess whether batching strategies improve throughput without unacceptable latency increases. Benchmarks also allow comparisons across systems, tools, or configurations, informing decisions about which approaches to adopt. Just as benchmarks drive progress in accuracy and safety, they provide the evidence base for performance engineering, linking optimization efforts to concrete results. Performance optimizations must always account for security implications, since shortcuts in design can inadvertently weaken protections. For instance, caching improves speed but may expose sensitive data if access controls are not applied rigorously. Similarly, concurrency and asynchronous processing can create vulnerabilities if synchronization mechanisms are poorly designed, leading to race conditions or unauthorized access. Compression techniques, if misconfigured, may leak information through side channels. Engineers must therefore design performance strategies with security in mind, ensuring that gains do not come at the cost of safety. In regulated industries like healthcare or finance, performance improvements must be validated against compliance standards, proving that security and privacy protections remain intact. By embedding security into performance engineering, organizations ensure that efficiency enhances rather than compromises trust. Reliability interacts closely with performance, as systems must balance speed and efficiency with resilience. Performance designs often incorporate retries, fallbacks, or circuit breakers to handle failures gracefully. For example, caching strategies may include backup retrieval mechanisms to ensure that stale data is not served indefinitely. Concurrency strategies must include safeguards against overload, while streaming outputs must be designed to handle interruptions without losing context. Reliability patterns and performance optimizations are not independent, they reinforce one another. An efficient system that fails unpredictably undermines user trust, while a reliable but sluggish system may frustrate users. Performance engineering must therefore account for reliability from the outset, ensuring that systems remain fast, scalable, and dependable under all conditions. Human experience factors remind us that measured speed and perceived speed are not always the same. Users judge systems not only by how quickly they respond in milliseconds, but also by how smoothly they deliver interactions. Streaming, for example, improves perceived speed by providing incremental outputs, even if total computation time is unchanged. Responsive interfaces that acknowledge requests promptly, provide progress indicators, or deliver partial results can create the impression of speed and attentiveness. Conversely, silent delays, even when short, may feel frustrating or untrustworthy. Performance engineering must therefore account for psychological as well as technical factors, designing systems that feel fast and responsive to humans. By aligning optimization with perception, engineers create experiences that foster satisfaction and trust, even in complex systems. Industry applications highlight how performance engineering strategies translate into practice. Chat assistants depend on streaming to create natural, conversational interactions, reducing the perception of lag. Recommendation engines rely heavily on batching and caching to serve millions of users simultaneously with personalized results. Fraud detection systems depend on concurrency and resource allocation to analyze massive transaction volumes in real time. In each case, performance strategies determine whether AI systems are usable at scale. These applications demonstrate that performance engineering is not an abstract concern, but a practical discipline that underpins nearly every successful AI deployment. Without caching, batching, streaming, and concurrency, many of the AI-powered services we take for granted today would be too slow, expensive, or fragile to operate. The cost impact of performance design is significant, as efficient engineering directly reduces infrastructure expenses. By maximizing hardware utilization and reducing redundant computation, organizations cut GPU and CPU costs, bandwidth charges, and storage requirements. For example, batching strategies allow more queries to be processed per GPU cycle, reducing the number of GPUs needed overall. Edge deployment reduces bandwidth costs by processing locally. Even small improvements in latency can translate into major financial savings at scale, especially in cloud environments where usage-based pricing dominates. Performance engineering is therefore not only about improving user experience, but also about financial sustainability. Efficient systems enable organizations to deliver high-quality AI services without unsustainable cost structures, ensuring that innovation remains accessible and competitive. Future directions in performance engineering point toward more automated and intelligent optimization systems. Advances in autoscaling allow infrastructure to expand and contract dynamically based on demand, reducing waste while maintaining responsiveness. AI-assisted performance tuning promises to identify bottlenecks and propose optimizations automatically, reducing reliance on manual configuration. Dynamic batching and caching strategies may evolve to adapt in real time to workload patterns, maximizing efficiency without sacrificing latency. These innovations will make performance engineering more adaptive, less labor-intensive, and more effective. At the same time, organizations will face new challenges in ensuring that automated optimizations remain transparent and aligned with human goals. The trajectory points toward performance systems that manage themselves intelligently, freeing engineers to focus on higher-level design and governance. As AI systems scale, the connection between performance engineering and cost engineering becomes increasingly clear. Performance determines how efficiently resources are used, and cost engineering ensures that those efficiencies translate into financial sustainability. Techniques like caching, batching, streaming, and concurrency reduce infrastructure strain, while cost engineering frameworks track the savings and allocate resources strategically. Together, they form a feedback loop. Performance optimizations reduce expenses, while cost engineering ensures those savings are reinvested effectively. This connection highlights the integrated nature of AI lifecycle management, where technical and financial concerns converge. By linking performance and cost engineering, organizations create systems that are not only scalable and responsive, but also affordable and sustainable in the long term. Performance engineering, then, is the discipline that ensures AI systems remain efficient, scalable, and user-friendly as they move from research into deployment. Strategies like caching, batching, streaming, and concurrency provide the technical foundation, while monitoring, reliability, and human experience design ensure that optimizations deliver real-world value. By balancing latency with throughput, embedding security into design, and aligning technical improvements with user perception, performance engineering transforms raw computational power into trustworthy infrastructure. Its importance cannot be overstated. Without it, large-scale AI systems would collapse under their own weight. With it, they become the engines that power interactive chat assistants, global recommendation systems, fraud detection pipelines, and countless other applications. Performance engineering is not optional but essential, making advanced AI sustainable, responsive, and reliable at scale. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.